Color perception requires a light source, an object, and an observer. A light source emits white light containing the visible color spectrum. This visible spectrum is measured in wavelength units called nanometers. There are many types of light sources, and each one has a unique wavelength. An object modifies light by absorbing and reflecting light. The light reflected by an object is an object's color. The amount of light reflected by an object can be measured at each wavelength and can be represented spectrally. A human observer's eye interprets color through light-sensing cells known as rods and cones. Rods primarily respond to light levels, while cones respond to color. There are three types of cones sensitive to specific wavelengths in the visible spectrum: red, green, and blue. Electrical impulses within these cells are then transmitted through the optic nerve to the brain for interpretation. Objects change color as their size changes. The area of the retina that collects light is represented by a 2-degree and 10-degree model. Color perception changes slightly between these two observing angles. How big are 2 degrees and 10 degrees? At arm's length, 2 degrees is about the size of your thumb, and 10 degrees is about the width of your fist. Color can be measured and communicated through the use of a spectrophotometer. A spectrophotometer works by flooding white light onto a sample. The light is then reflected by the sample and passes through interference filters, where only the color of the sample reaches the filters and all other wavelengths are reflected away. The wavelength representing the color is transmitted to a photodiode, which converts it to an electronic signal, which displays its spectral wavelength. All colors are organized in 3 dimensions: lightness, saturation, and hue. Lightness, also known as value or tone, is the brightness of a color. Saturation is the intensity of a color. Hue is a color or shade. LAB color space is a 3-axis color system with dimension L for lightness and A and B for the color dimensions. The LAB color space is the most exact means of representing color and is device independent. The L value represents the lightness axis, where 0 is black, 100 is white, and 50 is middle gray. The A value represents the red-green axis, where positive values are red, negative values are green, and 0 is neutral. The B value represents the blue-yellow axis, where positive values are yellow, negative values are blue, and 0 is neutral. All colorimetric values like LAB are calculated from the spectral signature of a sample under a specific light source, known as an illuminant. The choice of illuminant adjusts the calculated colorimetric values to reflect what the color would look like under different sources of white light. Some common illuminants include D65 or noonday light, F2 or cool white fluorescent, which is common in most offices and stores, and illuminant A or incandescent lighting used in most homes. Objects that match in color under some lighting conditions may not match under others. This phenomenon is known as metamerism. Lighting conditions and its effect on color appearance can be demonstrated in the following illustrations. Daylight is usually perceived to be more neutral when comparing color versus other illuminants. The graphics arts community has chosen illuminant D50 or daylight 50 with a 2-degree observer as the agreed-upon standardized viewing condition for appraising color. When providing color information for matching, it is important to define the numerical LAB standard values for color, as well as the illuminant and observer information used to measure the color standard. Using a standardized method for communicating color improves the ability of the viewer to interpret the color consistently.